our contribution was to propose different null models and then see how these models perform when applying modularity. And it does have some certain properties which are much better than the conventional null model that was proposed. So the null model is supposed to reflect the underlying topology of the original graph, but randomizing the models. Well, in some cases, often actually, the conventional model fails to do so because it assumes self-loops. Most typically, from what I've seen in practice in brain networks at least, you don't assume self-loops in the nodes in your graph, you assume connected areas. But in this case, the connection between I node with itself would be ki squared by 2m, and this is always positive. So basically, this network is biased to always assume some self-loops, and this will result in certain cases into indivisibility. If we don't desire any self-loops, we certainly get the expected value to be 0 in this case. Another advantage that we have is that we can handle negative edges. So an assumption that underlies this conventional model is that all edges are positive. And when you try to introduce negative edges because of the product, the sign changes randomly, arbitrarily, and you get a structure that really doesn't reflect any models or some other meaningful structure. However, in our case, even with negative edges, we can still see this is the adjacency matrix, and you can see a couple of models popping out of the structure, which eventually modularity will resolve them and separate them. And finally, I'm talking here about flexibility. I presented this general formula before. You have the mean and the variance, the covariance matrices. And you can introduce some prior information to your null model if you want. For example, if you can assume, if you know that because of measurement error some edges suffer from more variance than others, you can incorporate that in your model. We haven't played with this, but the potential exists, and we can explore that. So apart from the properties, let's see how the method performs. So we created a small simulation with a couple of modules. One had 12 nodes, the other had 8 nodes, and this was the adjacency matrix that we simulated. You can clearly see these models here. And our null model gives this as the difference between the original and the expected graph. And this is the conventional model. And you can see here that because of this limitation that I mentioned with self-loops, this diagonal here has strongly negative elements, and that's because even though the original graph has 0 self-loops, the conventional model has positive self-loops, so this difference becomes strongly negative. And because this becomes strongly negative, and overall we maintain the whole degree, in other words, the total sum of edges, everything else becomes positive. And it may look prettier because this is more intense color. However, what really happens is that these edges that would normally be between models become positive in this case because of the bias. And in this case, you reach something called indivisibility, basically. You cannot partition this graph anymore, you reach the limits. And that's what we really saw here. We have a very good performance in our case, but the other method degrades as you introduce more variance in the edges. We were also interested to see how these expected networks relate with actual rewiring schemes. If you take a graph and start rewiring by preserving the degrees of the nodes, how close is this network with what we have as an expected network? So we have this distance here from the randomly rewiring network. We use the method that is described in Maslow to do the rewiring, which involves getting 2 nodes and that are connected and then just switching the edges. Instead of connected this way, they're connected this way, and you repeat this again and again and again. And so in this case, you can clearly see in this graph that the conventional model, that definitely doesn't make sense to me because I was moving these things around. Can you please ignore that and consider that the playing with PowerPoint too much. So this is the conventional model actually, and the conventional model is really far more distant from the rewiring scheme than the model that we proposed, either assuming Gaussian distribution or assuming actually that was the Bernoulli and that was the Gaussian, so they were really, really close. So the idea behind this is that the expected graph that we proposed is much closer to a random rewiring scheme if you were to do all the effort computation to do that than the already existing model. And we applied this method to partition graphs on a structural network, a network described in this paper, which is basically a parcellation of the cortex into 66 ROIs using free surfer. And so we have a 66 node graph representing structural connectivity in the brain following the fibers. And that's a visualization of this network. So that was done with directly see that this one is a bit more symmetric than that one. You can see some structures that don't relate in both hemispheres. It's more clear to see in this view, which for every ROI identifies the hubs. So larger circles indicate the hubs, important regions in the graph. Most of the shortest paths go through these nodes, basically. And you can see that our method produces more symmetric results, especially in this area, the Queen's area, which is quite popular for resting networks, I know, than the other method. So that was also encouraging, but of course we don't really know the ground truth for these cases, but symmetry is always nice to validate methods. And all that was before was about undirected graphs. We then expanded this into directed graphs, which is nothing more but networks with directional edges. And let me just introduce notation here. Instead of having the whole degree, you have ki in and ki out. So the in degree and out degree, the sum of edges going inside and outside. So for the undirected graph, we have these two models. And for the directed case, these papers actually proposed this null model, obviously thinking in terms of this idea, ki, kj, you have now ki out to ki in. I don't really have an intuition to support this model. However, this model follows again the same idea of expected edge given the whole degree sequence, the in and out degree sequence. And similar to before, we had an expression for the Gaussian case, we have a new expression for the Gaussian case, which becomes a bit more complicated but still somewhat organized, I believe. And before showing some results on this, one more idea on working with graphs is information flow. It was actually suggested that the previous methods of partitioning were finding information flow, how edges are connected directional one another, but I don't think this is the case based on our findings. For information flow, what you really want to do is maximize the edges from one module going to another one, and at the same time minimizes the edges from the module 2 to module 1. So you would be organizing the nodes in these modules so that you would maximize information flow downwards. And the way you really want to do that is if you see this affinity matrix here, you really want to maximize these elements and minimize these elements by partitioning the graph. And you can compare this with how modularity was working before. Modularity basically maximizes the within edges and was penalizing the between module edges to find the community structure. Instead here we want to find how information flows from one cluster to another. And this is turns out to be quite straightforward to do. If you have this group indicator vectors having values +1 and 0 to indicate either you're in group 1 or group 2, then this quadrants basically correspond to these expressions here. And if you do a simple change, so if you place this group indicator vectors with the vector S, again with plus and minus 1 now, it really simplifies into this quantity. So maximizing this information flow is the same as assigning all the nodes with positive delta k, basically higher outgoing edges than incoming edges, assigning all them into one module and assigning the remaining ones to the other module. So that's really straightforward. Positive delta k is one group, negative delta k is the other group. And we did a very simple simulation to see how all these ideas work in the brain. So we simulated 4 sources, 2 in the occipital, parietal, however you want to call it, and 2 in the frontal lobe. And there was an interaction from the frontal to the posterior source in low frequency, and there was another 2 more interactions from posterior to anterior in high frequency. That was simulated with a 4th order AR model, and then we between all the nodes in the brain and try to segment this graph. So this is the interaction that we enforced. And these are the results that we got. So we separate the analysis for low frequency and for high frequency. And first we applied the graph partition scheme, which really separates hemispheres in this case. And unfortunately, MEG has low resolution, so this is a consequence of that. So when you do minimum maps, you really put things together, but we still identify a couple of networks over here. And when we apply the information flow within every module to see how information is transferred within every module, we really identify the proper way of having an information source here going to information sink, and correspondingly here from source to sink, and so on and so forth. And we did one more thing that I didn't mention, is that this is a binary map for information flow. We can go and for every element we can measure how much information goes to the other cluster by summing the edges. And you see that this was a pretty good description of the transfer of information. And the end result shows more or less what was the structure of the original network. So we recovered this transfer, this interaction, and the other 2 in the high frequency. That's, as you can see, it's a simulation that remains to be seen how these methods do in real data. And these are pretty new results. I didn't mention that before, but these are the relatively new things that we're doing in USC now, so we don't have much analysis for this. And the latest one that we've been thinking, many ideas simultaneously, is how to evaluate statistical significance of these partitions. So when you see 2 modules and when you maximize modularity, do you want to cut basically these connections and define 2 modules or not? You should do it statistically, of course, and you should not just do it by an increase in modularity, because that can be statistically insignificant. So the whole idea goes to go on and do a partition only if modularity is statistically significantly increasing, because every time you try to maximize this. And to do that, ideally you would go and partition random graphs and see how much modularity increases in every single one of them, get a histogram, and then decide what constitutes a significant increase in modularity. That can be time consuming. Instead of that, it would be nice if you had an analytical solution. And we did observe that the maximum making value of this matrix actually follows a gamma distribution with parameters A and B that we solved numerically to have these values depending on n and sigma, the size of the network and the variance of the edges. So we haven't really applied this anywhere yet because that's really recent, but there seems to be a clear way of partitioning a graph statistically guaranteeing significance. And based on the equation before, we move by bipartitioning again and again a graph, and in every step we can check whether we want to statistically proceed with a partition or stop at this point. And this problem is much more important when you have really large graphs, because large graphs have so many nodes that randomly you can end up with good-looking partitions, but that doesn't really mean that there is an underlying structure. There are just so many ways to partition a graph that some of them will work for you. So it is really important to do these things, which hasn't drawn much attention in literature, and I think it is important when you represent networks and partitions to make sure that they are statistically significant. And so I am concluding with this, and if you're scared, the other parts of the talk are faster, so it shouldn't take so long. So the second part is partial phase locking value, and the idea is the following. A very common analysis is synchronization analysis in brain maps. You get time series with a Hilbert transform and any other transform, you can get the phase, the instantaneous phase of signals, and then you can compute the phase locking value, expected value of e to the j difference of the phases. And this, strong phase locking value is an indication of communicating signals. However, what do you do in case you have a third source? And I believe in most cases, you must have one in the brain. You need something called partial phase locking value. You need to condition partial coherence or partial correlation, but it's not so straightforward to get partial phase locking value. And we searched the literature, and what we found was one work proposed by Cadio that uses this multivariate model of phases based on some physical system of oscillators, coupled oscillators, and considering angular velocity and so on. Basically, it's an existing physical system that would normally obey this multivariate phase, and K would indicate the coupling between the oscillators. So they proposed this model, which worked quite well when it came to this physical system, with a question mark about other physical systems though. And there was another method which is based on a very simple intuition. If you have the spectral matrix and you just invert it, you really get a scale version of the partial coherence. That's known, maybe not so popular, but that is a fact. So for nonlinear systems, they assume the following, that if you have the partial phase locking matrix and you invert it, you could get the partial phase locking value. That may be approximately true, and it is actually approximately true, surprisingly. The motivation that they gave in the paper was not very satisfying for me, but also this step here assumes Gaussianity. And if you are to assume Gaussianity, then how about going and analytically deriving some equations, and that's what we actually did with some effort. So we had this cyclic multivariate Gaussian model that has as elements the analytical signal of our time series. The only assumption that this model has is that you have n Gaussian sources. And from these you can have this model, and sigma is the covariance matrix, and Kij here would be the true coupling between the signals. And there were pages and pages of analytical derivations which you don't want to see, but we did get some expressions for the several quantities, like the marginal distribution of amplitude, the distribution of the phase, marginal, and also the partial phase locking value. So I'll show you in the next two slides these A and B quantities. And this is quantity A, the marginal distribution of phase. And yes, it looks complicated. We did feed this distribution on electrochromatographic data from an epileptic patient from Cleveland Clinic, and the histogram of the phase difference is in black color for the empirical data. And when we feed it the Gaussian distribution, it gave a really good fit for this particular case. I don't want to make an argument that overall it fits. We need to test this out, but there are certain data that this model fits quite well, versus the von Mises distribution here, which is the analog of the Gaussian distribution for circular data. And it so happens to be the distribution that the Cadio model becomes in the 2D case and not in the multivariate case. In this case, that gave a more poor fit. So that was encouraging for the marginal distribution phase. And here is the partial phase locking value. And yes, it is a bit complicated. And you also have this hypergeometric function, which I haven't heard before. So we had a very efficient student in USA doing all this analysis, Sergei Aidore. And so hoping that this signal is good and useful, we tested this function is good and useful. We tested it with a very popular system, the Osler oscillators. They're often used in periodic systems to study the behavior. So it's described by this equation, and all you really need to see here is that this quantities epsilon ij force connection between the oscillators. And that was what we modeled in this case. There was a connection between 1 and 2, a connection between 1 and 3, and nothing between 2 and 3. And so we expect to see that if we were to do partial phase locking values, should not see anything here. But we should see the connections in 1, 2, and 1, 3. And these are the results that we got. So if you were to apply phase locking value blindly, ignoring any third sources and so on, you would really get high phase locking values in all quantities. So, and including this one here, which is of course a false positive because of our model. We applied Cardew model, which was optimally describing a physical system of oscillators. However, in this case, it did fail. So it was actually quite similar to our surprise to phase locking value, and this quantity is also high. And I will conclude briefly discussing the idea of canonical correlations, because I promised I would do so. So the idea is that you want to find how frequencies interact between different brain areas. Most methods in brain connectivity really work on individual frequencies, such as phase locking value or coherence, identify relationships in a specific frequency. But what if you want to find how frequencies in this area best predict frequencies in another area? Well, the way to, so in such case you have data like this. You have molecule trials, and you would measure different frequency observations in one area, and you would measure different frequency observations in the other one. You want to find how these matrices basically relate. The way to go with this is to really get the expansion of the regular correlation to multivariate cases, and that is called canonical correlation. So what you really want to do is you want to maximize this quantity. You want to find vectors A and B that when they are multiplying these matrices, basically when they are weighting frequencies, they maximize correlation between them. So maximally weight frequencies here to best predict a weighted sum of frequencies over there. This is a very simple idea again. However, it did take a lot of effort to do proper statistical analysis with these quantities. And it's better shown if I show you a simulation for that. So we simulated 3 sources. The third source was interacting with the first and the second, and notice the different frequencies. The relation actually was a power-to-power interaction and not in the same frequency. So coherence in this case, for example, would be 0. So what we did is we assumed to have a seed over here, and we computed the canonical correlation to every other location in the brain. And you can see that canonical correlation indeed maximizes in the desired location, and also some other undesired locations in this case. And we also found an analytical expression for this map before. It follows the chi-square distribution, and therefore we were able to convert this to B values and then apply fast discovery rate correction for this map. And you can see clearly now these areas identified, which include true and false interactions. This one is obviously from linear mixing from the MEG data. But what we found out as well in this case is that when an interaction comes from linear mixing, A and B vectors tend to be parallel. The intuition behind this is that linear mixing means the same time series are in both sides, and therefore the same frequencies in both sides contribute to the interaction. Versus when you have a true interaction, these vectors tend to be not parallel. And thus, if you enforce a statistical criterion for this, you can get rid of these sources, and ideally at the end you should have only the true interactions. So this was the idea, and then of course you can go and see these vectors A and B and identify which frequencies contribute to the interaction. So alpha frequency here, as simulated, was interacting with beta frequency here, and alpha again was interacting with gamma over there. That was the original simulation. And we also applied this to experimental data. That experiment was done by Karine Terby in France, in Paris. The subject was looking at a rotating cube and trying to counteract the random movements of this cube. So it was a visual motor task, and we had two conditions, the task and versus the rest. So what we did was we used the visual motor data, and we applied the seed over here, and we computed the canonical correlation map in every other location, and then with the test that I described before, we threshold this map for statistical significance and linear mixing, and what we ended up with was bright spots in the visual cortex. And of course, reality doesn't follow your simulation, so the pattern of frequencies involved in this interaction is much more unclear than in simulated data. So there's a bunch of frequencies involved here. And I would believe that this concludes the talk with a nice picture, I hope. And I do want to acknowledge this research group in USC that I was until recently, led by Richard Leahy. And I also want to specifically mention the three students, Yuteng Chang, Said Laidar, and Juan Poleti Soto, that were heavily involved in